In a previous video, we saw the role played by the DC-DC converter of the TCON board in the production of the 4 voltages necessary for the operation of the LCD screen. Now, we are going to look at another essential component of this board. It is an integrated circuit known under the term of gamma chip. This chip plays an important role in the control of the quality of the image. The so-called gamma chip is actually called gamma voltage generator. In addition to the generation of voltages, it can include other circuits such as a VCOM calibrator, and it can integrate memories. When this chip is defective, an altered image appears on the screen. Among the signs that indicate that a gamma chip is defective, we can observe a whitish image, missing colors, saturated or inverted. Sometimes, the display of colors is badly shaded. This phenomenon is known under the term of solarization of the image. Basically, gamma is the third letter of the Greek alphabet. This alphabet is very used in mathematics. The term gamma was adopted because it actually represents a mathematical value. To better understand the use of the term gamma in all that concerns the display and quality of images, a small reminder of mathematical definition is necessary. The following mathematical expression reads, x power n or x exponent n. This means that x is multiplied by itself n times. If n is equal to 0, x is equal to 1. If n is equal to 1, x is equal to x. If n is equal to 2, we get x squared, and so on. Let's try to represent on a graph the following function. On the abscissa axis, i.e. on the horizontal line, is noted the value x. On the ordinate axis, i.e. the vertical line, is noted the result y, which is equivalent to x power n. Now when the exponent n is equal to 1, we obtain on the graph the following values. If we draw a line connecting all the points, we observe that it is a straight line. In other words, it is a representative curve of a linear function. Now, if we change the value of the exponent n to 2, we get the following results. If we draw a new curve connecting all the results, we see that this curve is no longer linear. This type of curve is called exponential. It is this type of curve that we find in the operating mode of the old cathode ray tube television sets. And the concept of the so-called gamma curve comes from there. The display of the image, in the old televisions with cathode ray tube known under the term CRT, required to bombard with the help of an electron gun, the surface of the cathode ray tube. This last one was covered with a sensitive material, made of a phosphorescent powder colored in red, green, and blue. Magnetic fields were used to concentrate and direct the electron beam towards the pixel to be lit. It is the impact of the electron beam that illuminated the phosphorescent powder and gave the color to the pixel. The image on the screen was reconstituted, giving the right colors to the right pixels. Here is what the curve of the graph representing the brightness of the screen of the cathode ray tube according to the received voltage looks like. We find the same type of nonlinear curves seen previously. This is due to the fact that the quantity of electrons emitted is not proportional to the voltage received. So if the electron gun receives twice the voltage, it will not produce twice the light intensity. This is why a CRT screen tends to darken the image it displays. In our formula, the letter n is replaced by the lowercase of the third letter of the Greek alphabet, which is gamma. In this formula, the gamma is an exponent. The formula of the type y equals x power n is called in mathematics a power function. In technical language, we say that the operation of the cathode ray tube follows a curve with a gamma equal to 2.2. And to describe the visual sensation of the brightness of a surface, we use the term luminance, and it is represented by the letter y. The video signal captured by the camera does not have at all the characteristics of the curve displayed by the cathode ray tube. If we represent this signal on the previous graph, we see that the curve is linear. This means that the sensors of the video recording devices have a linear response with a concordance between the value of the voltage and the light signal captured. So to correct this technical problem and avoid increasing the manufacturing cost of CRT televisions by adding electronic components of compensation, it was chosen to make the correction by acting on the video signal by adding a certain value to it. This value is called the gamma correction. It gives the following curve. This curve is this time of logarithmic type. It is a reciprocal curve of the blue curve, which represents here the gamma of the CRT television. Here, the value of the gamma correction is 0.45. This figure is found by performing the following operation. 1 divided by 2.2, which is the gamma of the CRT television. So when the CRT television receives the video signal to which a second value has been added, that of the gamma correction, the screen will display an exact reproduction of the starting image. It should be noted that the image is pre-corrected on the light intensity captured by the device and before its recording. This operation carried out upstream and applied from the digital camera or the video camera in the form of a transfer curve which is the inverse of that of gamma. Now why we continue to use this technique of gamma correction, while CRT televisions are no longer manufactured. They have been replaced by LCD TVs which have a linear response like the video camera and as can be seen in this graph. One of the reasons was that it was necessary to ensure the transition and coexistence between CRT televisions and the new plasma and LCD televisions. Therefore, it was necessary to adapt the new technology to the video signal that includes a gamma correction. This is one of the reasons why LCD televisions were equipped with a gamma chip to take this parameter into account. Another reason was to take into account the fact that the human eye does not have a linear sensitivity to light. Take the example of lighting a torch in daylight, it will not improve vision and reveal more details of what we observe. On the other hand, lighting it in a dark place, the eye can distinguish more nuances because it has a better sensitivity to light for the darker nuances. Here is what the curve looks like on a graph representing the perception of the human eye of the perceived brightness, noted on the vertical axis, depending on the luminance, noted on the horizontal axis. The formula that relates the perceived brightness and luminance has been defined by the IEC, which is the International Commission on Illumination, also known as the CIE, from its French title, the Commission Internationale de l'Éclairage. The curve resembles that of the correction factor gamma. It is said that the sensitivity of the eye of the observer to light follows a logarithmic curve. The principle of gamma here is not used in order to correct a defect of the eye, but it is quite the opposite. The human eye has a better perception of contrasts and is more sensitive to small differences in brightness in dark environments than light. On this photo, the two small circles on a white background are the same as those on a black background, and yet the eye sees a different contrast between the two. So the concept of gamma correction has been kept to get closer to the human vision and obtain a good visual quality of the recorded signal. In practice, the digital recording of the image uses binary coding. In this language there are only two letters, or more precisely two numbers, 0 or 1. This elementary information is called the bit. The images displayed on a screen are made up of a very large number of pixels. Each pixel will be coded in binary language. If we use a single bit, there are only two possibilities. For example, the value 0 will be assigned to black and 1 to white. This is the so-called monochrome display made only of black or white. With 2 bits, there are more possibilities, and more exactly 2 to the power of 2, which makes it possible to code 4 colors. For a coding 4 bits, with the same formula, but here raised to the power of 4, gives the possibility to code 16 colors. For a coding on 8 bits, gives 2 to the power 8, which corresponds to 256 colors. With 24 bits, we reach more than 16 million colors. The increase in the number of possibilities of the colors thus follows an exponential curve. In computer language, a set of 8 bits represents 1 byte. Thus 16 bits constitute 2 bytes. 24 bits constitute 3 bytes, and so on. As we have seen before, each pixel is made of 3 colors, which are red, green, and blue. If each of these colors is coded with 8 bits equivalent to 1 byte, we obtain shades ranging from 0 to 255. This is equivalent to having 256 types of red colors, 256 types of green colors, and 256 types of blue colors. As in each pixel, there are 3 different colors, it will take 3 bytes to code each pixel to properly reflect all the nuances. When coding an image, there is an optimization of the use of bits to take into account the fact that the human eye perceives light and colors in a nonlinear way. With this coding, we assign fewer bits to the brightest images and more bits to the darkest images. In a PC screen, the image encoded according to this principle must then be decoded before being displayed on the screen. For this, the image is first stored in a buffer in order to assign new values. These new values are used to correct the image, because it should be remembered that during the recording the image was pre-corrected. The new values are assigned according to a correspondence table known as the LUT, which is the acronym for lookup table. On the first column are written all the input values, and on the second are written the new values. The LCD screen uses this table to make a gamma correction of the image. The subject is not finished. Other concepts related to the gamma chip will be covered in a future video. See you soon.